Hi, everyone, and welcome to another episode of the Go STEM Show. I'm Pam Piskridge, the Program Director for Gelfand Outreach. And on today's show, we are featuring the Mechanical Engineering Department at Carnegie Mellon University. We have 2 faculty members and a PhD student from the department. We also feature Mr. Manning's 4th grade homeroom at Community Day School here in Pittsburgh. Students sent in questions that they would like to ask our 3 guests. If you would like to send questions to Gelfand to our show, simply email them to the address that's on your screen right now. We look forward to hearing from you. Our first guest, Dr. Grande Gutierrez, studies blood flow, and her research helps doctors identify patients at risk. And I would like to welcome her to the show to explain a little bit more about her research. Dr. Grande Gutierrez.
Hi everyone, nice to see you all. So I'm Noelia Grande Gutierrez. I'm an assistant professor in mechanical engineering at Carnegie Mellon University, and I study blood flow using computer simulations. So the goal is that these simulations can help us understand cardiovascular disease and help doctors to get better diagnosis and better therapies for patients. So I grew up in Spain and I did my undergraduate in aerospace engineering, then my master's in biomedical engineering, and then I moved to California for my PhD in mechanical engineering. I love to travel and also Spanish food.
Sounds well-rounded. Our next guest, well, she can tell you a little bit about herself, but she started at Carnegie Mellon with the Gelfand Center a long time ago. And maybe she'll speak a little bit to how she started working for the Gelfand Center many moons ago. Dr. Nara is an assistant professor in the Mechanical Engineering Department whose research is in additive manufacturing and improving those technologies. I welcome Dr. Nara to explain more.
Thank you. Hello, everyone. It's nice to be here. I'm Sneha Nara. I'm an assistant professor in the Department of Mechanical Engineering at Carnegie Mellon University. Prior to this, I did my master's, PhD, and my postdoctoral training at Carnegie Mellon. I went away for 3 years and now I'm back again. So during my graduate school, I had an opportunity to volunteer through the Gelfand Center, and that was really exciting. Probably the first time I learned more about STEM outreach. So I'm originally from India, so I grew up in India, and then I came to CMU for my master's. My undergrad is in civil engineering, so where I learned a lot about structural analysis. But then I developed interest in manufacturing, which brought me into mechanical engineering. And now my research is mainly focused on additive manufacturing. And most of you know this as 3D printing. I specifically work with metals, whereas probably the printers you use at school are using polymers, it's plastic. And what we mainly do is we try to understand how the manufacturing process works, and we try to understand how the material responds to the manufacturing process, and then we combine these two to get a material with the properties we want. It's a pretty ambitious goal given the complexities associated with the process and the material, which is what makes our work very exciting and challenging at the same time.
So metals used for what purpose?
So we work with a variety of materials that have applications in aerospace industry, energy applications as well. So these could be alloys that are made of titanium, nickel, steel. So there are a number of combinations that we work with, like material combinations that we work with.
Thank you for sharing and thank you for being here. And then our final guest for today is also in the mechanical engineering department and also studying additive manufacturing. So let's welcome Alex Gorley to the show. Alex.
I'm Alex Gorley in the mechanical engineering department. I'm a PhD student and I do work in the Buth lab and the Cheyenne lab. And so I did my undergraduate at Duke University. I'm originally from the North Carolina area. And in undergraduate, I studied chemistry and mechanical engineering. I realized that I really like to make things, and that kind of pushed me down that path. And partway through, when I was initially doing chemistry, I saw kind of some of the things the engineers were doing, thought it was really cool, got into that, and that like desire to kind of build things developed into the additive manufacturing or 3D printing that I'm doing now. And so with that, I'm now doing work with ceramic additive manufacturing, which is kind of like materials like glass and stone, things of that nature, looking at building up structures with that. It's a relatively new field, so figuring out all the different challenges with just initially getting it done is a lot of the work that we're doing right now. So.
And I have to put in a little bit of an advertisement for our students. This spring, Alex will actually be teaching a course for the Gelfin Outreach Saturday series classes, and it is on additive manufacturing and available for our 3rd through 5th graders. So watch our website and sign up for Alex's class if you're interested in his research. So Mr. Manning's group phrased their questions in the form what they would like to know and ask each of you. So let's start with Dr. Grande Gutierrez. Ella wants to know what makes you want to be an engineer.
Well, growing up, I was always very intrigued about how things work and how things are made. So I think that becoming an engineer and being able to act on that process kind of like felt natural. So I decided to go down that path. I always knew science and math were of interest, and being able to build things and understand what are the insides of things that you see every day was like really attracting to me.
So what kinds of things did you build as a child?
I don't know, like construction sets, like bridge type of constructions. And also my father was an electrician. So like we used to do a lot of like electric, like building a house with some lights and things like that. Yeah.
Good for our future engineers to know. Start building now. Dr. Nara, what makes you want to be an engineer?
So I was good with math and science. And at the same time, like my mom was a teacher. So I have developed, like I always like the idea of like talking to students, like teaching something. But I did not really think about engineering until my 12th grade, where I had to make a decision about it. So I primarily chose civil engineering because I was inspired like by my friend's father, who was a civil engineer, and my interactions with him and learning about construction and how things come together with respect to like how we use math in solving a problem, and how do we understand materials in solving a problem. So like material properties in solving a problem. So they pushed me towards, when I say push, they inspired me to pursue civil engineering. And through that, I went into mechanical just because of the variety of options that were available for mechanical engineering major.
So a strong interest in math led to engineering.
Yes.
Very nice, very nice. Alex, what makes you want to be an engineer?
So probably one of the biggest things is seeing what everybody's doing. When I was initially getting into engineering, one of the things that drew me to it was just seeing people do things with cars, with spacecraft, with planes and things like that. And it just seemed really cool. And with engineering, you learn a lot with how a lot of these different systems works, or how they work. And with that, you can do a lot of cool things. And so that's ultimately what kind of drove me to get into engineering and what keeps me here.
We're great. Glad you are here. Okay, this next question is from Ava. And Ava wants to know, along those same lines, what is your favorite thing about being an engineer? Alex?
Yeah, so my favorite thing about being an engineer is being able to build things. I like being able to have something at the end of the day that kind of shows like what I put my work into, and just to have that physical thing there. And so, yeah, with engineering, one of my favorite things is to build stuff. And that's ultimately why I decided to get into 3D printing with additive manufacturing.
I know in artwork, artists usually sign their pictures. Do you sign your 3D printed material?
I haven't done that yet, but that's an interesting thought.
Okay, Dr. Grande Gutierrez, what is your favorite thing about being an engineer?
So I think that there's always something new to learn, and there is always a new problem to solve. And I think one of the best things is that you solve problems that in general help improve people's life in many different ways that you don't even realize. Like, since, for example, my work is in the medical field, so I can contribute to advancing medical diagnosis, but engineering can be applied into building new and like better transportation, or like producing energy in a cleaner way that like helps keep the planet healthy. So there are so many problems that you can work on, and every day is changing. Every day there are new things coming up. So I find that very exciting.
So our students should be listening. There's a lifelong learning process that takes place. All of these people on the screen are learning new things every day.
Every day.
And then Sneha?
So like Alex and Noelia covered like two different aspects. So along with those, what I would like to add is just the difference we make. Like if we go to a doctor, like that is something we experience personally, but engineers' contribution is like everywhere. Like if things are working well, if your laptop is working well, if the building you are living in is safe, or if you are on a flight and it's a safe flight, all the aerospace components and how they are made and how they are tested, how they come together. So like I first realized like the amount of impact an engineer has probably in my master's. Until then, I did not really think in detail about it. So like for doctors, we experience it like on a personal level, but engineer, I think, is more like the number of lives we can touch with the work we do is very high. Like will be on the order of thousands and maybe more than that. So that's why I like to be an engineer.
Yeah, wonderful. You can't avoid engineering. Everywhere you look is there's something engineered. All right, the last question for all three of you. This is Oliver from Mr. Manning's class. Oliver wants to know, what is the strangest or weirdest machine you've ever worked with in your career, whether it was high school, all the way through? What's the weirdest or strangest machine you ever worked with? Dr. Nara?
I thought hard about this question, and nothing strange or weird, but I feel very fortunate to have worked with like the coolest manufacturing machines, right? The metal 3D printers, like they are not easily available, but I had the opportunity to work with them since the first year of my grad school, and now I have my own machines in the lab. So probably the metal 3D printers are the coolest machines I worked with. I'm not able to remember any weird or strange machines.
So what's the basic difference between the metal 3D printer and the polymer 3D printer?
So in the case of polymer 3D printer, you are using plastic. In the case of metal 3D printer, you are using material like steel, or there are some printers that can print with gold, silver. So these are essentially metals. So the conditions under which you do the fabrication, that is printing, are different when we take a polymer printer versus a metal printer.
Are they different in size?
Yes. So in both the printers, you can have a number of sizes where you can print very small parts from the size of this plastic cap to like very big parts that are on the order of meters. So size wise, both polymers and metals are capable of working with different size components. But when I say conditions, when we are printing with metals, we want to make sure there is no contamination. So the conditions that are required to perform the printing are different from polymers. And the way we are doing the layer by layer fabrication in 3D printing, right? Like you are printing one layer at a time. In the case of polymers, you heat the material to soften it so that it becomes stretchy and you can place it in any way you want to print that complex part. Whereas in metals, we typically melt the material. That is, it becomes a liquid. And we melt wherever we want. And that's how we get a liquid pool, and that liquid solidifies, that is, it cools and becomes a solid to form the actual part.
So you must have a really large lab.
So we have, at CMU, I have like a machine in my lab, but we have common additive manufacturing facilities. So there is one big lab on the main campus, and we have a new facility at Mill 19. That will be a great lab tour actually for school kids. So we have 2 labs here for metal printing.
So you're volunteering to give those tours.
Yes, I'll be happy to. And you can actually see in my lab, we have a robot which does the printing.
Oh, nice. I'll have to stop by one day.
Yes.
Dr. Grande Gutierrez, how about you? What was the weirdest or strangest machine?
Yeah, I've been thinking also a lot about this. I don't think I ever encountered something super weird, but I would say that I've had the opportunity to work with like really big machines, like exceptionally big. For example, when I graduated, after graduating from aerospace engineering, I worked at a mechanical testing lab. And in this lab, we were testing aircraft parts. So for example, something that goes into the wing of the plane. So these are huge parts, and we were testing typically new designs or new materials to make sure that they were okay for flight conditions. So we used this massive machine that was as tall as approximately a 2-story building. So that's a very unique type of machine, not so many out there. I thought that was pretty exceptional. So now I work mostly on the computational science side of things, so mostly working with computers, but I have the opportunity to work with now like really, really big computers. So the computers I typically use for my simulations are as big as a full room of computers. I don't have physical access to that, but I can, through my laptop or through just like a PC that as similar as what you can have at home, I can get access to all those computers at the same time and then have all this computational power just sitting from my desk.
Wow. And is your lab huge in size, or are you just in that office with access to all those larger facilities?
Right. Yeah. So we are not huge in size because we only need like just a terminal point to access those computers, but the location where those computers are hosted is definitely really, really big.
Wow. Again, I'll probably have to visit your lab now too, after this is all over. Alex, I know you had race car experience, and I'm just curious to hear the answer to this question. What was the weirdest machine you worked on, or strangest?
Yeah. So again, with like a lot of the stuff that I've had the opportunity to work with, it's like a lot of it feels really cool. So like calling it strange or weird might not necessarily be the descriptor that I would put to some of these, but the coolest piece of machinery that I've had the opportunity to work with was a wind tunnel. And so with a wind tunnel, you put different objects in the wind tunnel and you kind of strap it in, and then you blow air across it in order to see like how the wind interacts with whatever you have in there. And so historically, there's been like a lot of tests with like airplanes and space shuttle parts in this, figuring out how that'll interact. And when I worked for a race car team, we had to know the aerodynamics of the car. And so we would put a full car in a massive wind tunnel that was the size of a warehouse. And we would have air blowing across it at 180 miles an hour to see how it would act at these high speeds. And then on top of that, in addition to just having the wind tunnel, when they recycled the air back through, the fans would actually heat up the system. And so they had to have additional components that cooled down the air as it went through. So it was just like this massive complex system that I had the opportunity to work with, which was just a lot of fun, being able to put a whole car into a wind tunnel.
Yeah, well, we know that that was pretty big too. Where did you do that? When you were at Duke?
So I did that when I was working for Germain Racing, which was a NASCAR team. They were actually the team that was bought by Michael Jordan. And with that team, there was a wind tunnel down in North Carolina that we were able to go in and pay by the hour for its usage. Because a lot of race car teams with NASCAR are located where I'm originally from in Mooresville, because that's where it originally started. So there's a good amount of facilities there for that sort of thing.
And you said right now you're working, your lab is in Scaife Hall?
So the Buth lab does work in the next manufacturing facilities. So a lot of the facilities in Hammerschlag, and then also Mill 19 with the 3D printers. But I also do some work in Professor Jayan's lab, which is located in Scott Hall.
Okay, very nice. And Alex, this next question is for you as well. It is from Tidar at Community Day, and he wants to know, how do race cars work?
Yeah, so race cars are very complicated systems, and it takes teams in order to go in and build different race cars. It's definitely not a single person sort of thing, because there's all these little different components ranging from engine to the suspension, so how the wheels kind of interact with the ground, and then like the wheel assemblies, so putting in brakes and things of that nature. And one group that I've done a lot of work with is like aerodynamics. So how we shape the car to interact with the wind as it moves. And so one of just the biggest general things with racing is thinking about how the tires push the car. And with this, Like you kind of think when you're trying to run and change direction and stuff like that, you're using your shoes to push off the ground. And with the tires, that traction with the ground allows us to start moving quickly or to change direction quickly. And so with that, there's a lot that kind of goes into that, and trying to make it so that with the engine putting energy into the tires to push it forward, aerodynamics actually pushing the car down to prevent the tires from slipping on the ground, suspension to make sure that everything's working properly and that you have the maximum contact. And so with race cars, you want to be able to accelerate quickly. So you want to go from slow speeds to high speeds in a short period of time. And with that, having that grip with the ground is everything. And even with like turning and stuff like that, you can think you're changing the direction of your motion. So having that grip with the ground helps you turn quickly and it helps you get going quickly. So that's one of the most general things with race cars. The tires are like some of the most important components, and a lot of the systems go into making the grip with the tires better. So yeah.
So it sounds like there's a lot more problem solving involved when you're creating a race car than just a regular automobile.
Yeah, or one of the things with race cars versus cars you see on the road is there's different requirements that they have to reach. And so with race cars, we want to go fast and we want to get going quickly and stuff like that. So everything we do in the car is to get it to move fast. With normal cars, they might not put as much of their resources and money with the particular car into making it go quite as fast, but you have all these different components and things like blinkers. Race cars tend not to have like blinkers and things, and you have air conditioning in cars. You don't tend to have those in race cars. And so there's a lot of other things that go into normal cars that race cars don't have. But race cars have like a very specific purpose, and that's to go fast, whereas normal cars have to get you places and have to make you feel comfortable getting there. So there's just a lot of different things that you need to balance between whichever sort of car you have.
Well, staying on that same topic, Asher wanted to know how race cars reach such high rates of speed. Can you talk a little bit more about that?
Yeah, so with race cars, as I mentioned, one of the big things is grip, and being able to turn. The speed at which you turn is dictated by how much grip you have. But when it comes to like top speed, like how fast the car can go, there's two big components that kind of come into that. And so you would think that the internal friction of the car would be a big issue, but when you get up to your top speeds, the two main things are wind and then how strong your engine is. So those are the two things that are kind of fighting against each other to reach your top speed. So one thing that you can kind of think about is like when you're in a car moving and you roll down the window, the air outside feels pretty strong. And especially like if you do it slightly on a highway, like the wind is just, it's intense. And so you just imagine that being applied to the entire surface area of the car, and you can kind of imagine it builds up, and it builds up quite quickly. And so with top speed, that's the thing that the car is having to fight. And so your engine has the power that's kind of trying to combat the wind hitting the car. And so with that, making the engine more powerful can get you a higher top speed, but then also adjusting the outside of the car so that the wind interacts with it less also helps you get a higher top speed. So those are like two of the main ways that we push cars to hit higher top speeds.
And students, don't go sticking your head out the window in the middle of a highway. Not a good advice. Okay, so this next question is for Dr. Grande Gutierrez. it is sent in from Shoshana, and she wants to know how a machine can predict heart disease. Very good question.
Okay. Yeah. So let's just start by when you typically feel sick and go to doctor's office, sometimes they would use a machine to take a picture of the inside of your body. So this is typically called a scanner. And then on those pictures, we can see the heart. Let's say we take a picture of your chest, so we can see the heart, we can see the arteries and the veins. So medical doctors typically would study these images and look for changes in size or the shape of your vessels. And that can be a sign of heart disease. But sometimes these pictures are not enough to decide, maybe because there is not so much change or because the specific presentation of the disease is not clearly seen in the images. We need more information about how is blood flowing through these vessels. So then in that case, computer simulation can help, because what we can do for example, what I do in my lab is we take those images and then we can build a 3D model of your arteries. So we can see, for example, the aorta, which is the artery that comes out of your heart and then feeds the whole system. It goes to your whole body. So we can image those arteries, and then we can do a computer simulation that will give us information about how the blood is flowing. So then we can measure the velocity, we can measure the blood pressure, we can measure the forces of the blood in the arterial wall. And using that information, then the doctors can take it and help with the disease, because this additional information about the function, about how blood is flowing, may help them understand what is going wrong. If the velocity is too low or too high, if the pressure is too low or too high, may be an indicator of heart disease. So it is something that you don't get from the regular image data, but you can get by using a computer and learning a little bit more about the physics of the blood flow and getting this information.
So, and that scan, is it a live scan, or are you simulating the movement? Is it a still picture or a moving picture that you're researching?
Yeah, it can be both. Sometimes they are able to take a moving picture, but many times the most common is that they take a still picture. But then we can also simulate the movement of these arteries. As you know, blood is pulsatile, so your heart is pumping, and then the vessels are moving during systole and diastole. We can incorporate information about the physics of the wall, the mechanics of the wall into our simulations, so we can have both the, let's say, the dynamic information and all, even from a still image.
And you are 3D printing these heart protocols?
I mean, I haven't used 3D printer a lot, but I think it would be really interesting too, because we should talk more about 3D printing, since there's a lot of 3D printing people in this show. But yeah, we have all the information that we need for doing a 3D printed version. I mean, I've had a few models 3D printed, but definitely we can do that. And we could even use some like VR, augmented reality type of technology to see what we get from the simulations on the 3D printed model, which I think would be really cool too.
And your when you identify a person, say, that's at risk for heart disease, what then does the doctor do with your findings?
Right. So what we do is still in a research state. So there are some applications that have been that are used in the clinic, but typically this is important in cases where it's not clear what to do. So doctors may want to get a bit more information before going into surgery and so on. So then they'll get additional information from the simulations to make their decision about whether to go into surgery or not. Another thing that can be really useful about the simulation is that, let's say that the doctor decides that you need to get surgery and maybe they need to do some modifications in your arterial tree and put a bypass or something like that, or take out a part of the vessel. So you can do that in the computer first and see how things are going to go. Maybe there are different options for your surgery, so you can try those out in the simulation and then look at the results and then decide what would be the best approach for each patient.
Oh, that's really cool stuff. Dr. Nara, this last question, I keep saying last, it's not the last question. There will be more questions. Hannah wants to know, what was your favorite build?
Wow, these kids have asked really difficult questions. What was my favorite build? There are definitely many, and I'm always looking forward to the next build we do. So since we are doing research, we have the opportunity to do some really cool builds. One thing that I really enjoyed was related to my research, where if you imagine like your hair right now, think of something that is 10 times smaller or thinner than your hair. So I was able to control the size at that small scale in the material that we are working with by changing how I fabricate using that material. So when I say change by how I fabricate the material, one way I would like you to think about it is like you're baking cookies in an oven. So there are some there are some controls that you change when you are baking cookies. Those could be like preheating the oven and then changing for the temperature at which you want to bake, for what amount of time you want to bake. So next time when your parents bake cookies or you bake cookies, what I want you to do is, you take it out after 5 minutes and then just poke at it and think, and then feel how it like what it feels like, the cookie material, right? The dough that is yet to set. And then do the same for small intervals over the baking process, and you will realize you can see the difference in the texture and the hardness, right? How hard the cookie is. So similarly, when we are doing manufacturing, there are some conditions that we can change in the process, which changes the structure of the material. Structure there refers to the size of the features that I'm talking about. So that's my favorite build. And I think it will stay as my favorite unless one of my PhD students now amazes me with a different experiment. So yeah.
And is that like, you said smaller than the size of your hair, is that sort of nanotechnology?
No, I don't think I can call it nanotechnology, because these are like, from my understanding, I don't think I can call it nanotechnology, because I'm still working with something that is big, but as I zoom in to that big thing, like that big part, as I zoom in, we go to that really small scale, and we were able to control the structure at that scale.
I think I get it. Thank you. Alex, back to 3D printing. How long does it take you to make something using additive manufacturing? And then this is a funny one. Ella also wants to know where you get your supplies.
So with additive manufacturing, the amount of time that it takes can vary quite significantly based on what you're printing, the material itself, and then the part that you're also printing. And along with this, the material that you use also causes the time to vary quite a bit because you have different types of 3D printers for different materials, and having the different processes can make time vary quite a bit. So with some more general stuff, like when it comes to like plastic 3D printing, I have a personal 3D printer at home, and I'm actually printing off Christmas gifts using it. And like per Christmas gift, it's taking about 12 hours to make a single part. So it goes for a while, but luckily it's the sort of thing where once the machine gets going, you can just leave it and it keeps going. With a lot of the stuff that we kind of do in the lab, where it's using kind of ceramic stuff, again, it varies based on the printer, but with some of the binder jetting stuff, so it uses a liquid binder to kind of stick powder together, and then we heat it up to help the powder fuse together, kind of like pottery does. With that, the initial printing itself can take 4 hours for small parts that we then can use to go and check different processing parameters and stuff like that. But when we put it into the oven, we put it in kind of overnight and we heat it up, and there's different processes that we can use with that. So the printing itself can take a few hours, and then the post-processing can take a good amount of additional time as well. So it varies quite a bit based on what you're printing and the objects that you're printing. But in terms of material, with plastic 3D printing, you can get a lot of material from different places online. Things like one of the most common ones is called PLA, polylactic acid. And with that, people sell it for about $30 for a kilogram of it online. With the powders and things that we use for the other materials in 3D printing, there's a bit more of a process for that, because dealing with powders, you don't want to inhale any of it. And so we have to go through some safety stuff in order to order particular materials, but there's individual providers that we can contact, a lot of whom are actually in Western Pennsylvania. So yeah, it's just an individual seller sort of thing.
So when you said that small thing can take up to 4 hours to print, approximate size of small when you said that?
So approximate would be, say, or so with the particular process that I'm referring to with binder jetting, you have a whole kind of platform and you have a nozzle kind of go over the whole thing so you can make many small parts at once. And that's kind of what we do for some of the initial testing with it. And with those kind of small parts, we can do like a centimeter by a centimeter by a depth of half a centimeter, we'll say. So like they're really small parts, but we can make a lot of them in a single go since we can do a whole sheet at once.
Yeah. You have probably much bigger machines than Ella has. So this next question is for Dr. Grande Gutierrez again, and it's from Hannah. And Hannah wants to know, how do you kind of build a spaceship, but then how does the spaceship make it up into space?
Okay, yeah, so I know a few things, but I want to mention, as Alex mentioned earlier, that building a spaceship is definitely not a single person task. It takes a huge team of engineers and other experts to build it, and also many steps involved. Typically goes design, analysis, testing, and fabrication, and some more testing, and then hopefully things work out, and then it's ready to go into production mode and actually build the spaceship that is going to go into the air. So the other important thing to keep in mind is that typically when you're building cars, you're going to build a bunch of cars, like thousands of cars. But when you're building a spaceship, it's going to be just one. And it's going to be like a huge thing. And sometimes it's even like one single use. So it's definitely like everything has to be perfect, right? So I want to mention a key points, and in particular regarding like how do they get into space. So one of the main key points of building spaceship is the propulsion system. So that is the engines. So first, you need really big engines that provide the necessary boost to make it outside the atmosphere. That is, you go out of the Earth, cross the atmospheres, and enter into orbit. Once you are there, because there is no resistance to the air, things become easier, so you don't need that many engines. Yet, spaceships typically carry some little boosters that would help you adjust the trajectory if you need to. In particular, if you're going into a long-term mission and you need to transfer orbit. Then there's obviously the structure is also a very important part because it has to withstand all the forces as you go up into the air, the control system, and the power to the power system because, for example, like spacecrafts typically will carry solar panels. So that way they can convert the sun's energy into electricity. And that's going to help you power the spacecraft once you are up in the space and also its equipment. So keep in mind that there's no gas station in space that you can just stop and fill up, right? So you need some alternative way of powering the spacecraft once you are up there. And the last thing I wanted to mention is that typically an important part of the spacecraft is the radiation and thermal protection. So when we are on Earth, the atmosphere protects us for harmful radiation, but once we are out of Earth, we don't have that protection anymore. So we need those shields to protect the astronauts that go into the spaceships, but also the equipment, which wouldn't work appropriately if they get too much radiation. And if we are designing a spacecraft that's meant to go back into the Earth, it needs to be protected because during re-entry into the atmosphere, it's gonna get really, really hot. So you need a thermal shield. And hot as in like a few thousand of Fahrenheit degrees. So this is really, really hot, like a fireball, pretty much, yeah.
Wow, that's some pretty cool stuff. The fact that the astronauts are in their capsule, there's enough electricity from those solar panels that can keep them. That is amazing to me that they figure out like how many solar panels would they need for, different. I'm sure it varies from mission to mission, but
yeah, definitely. Just keep in mind also when you're thinking about these panels, I mean, like, there are definitely also other equipments that they bring from the Earth that for auxiliary power. But when we are outside the atmosphere, the radiation from the sun is much more direct. So you are able to get way more electricity than compared to a solar panel that you have here, maybe in your house or something like that.
Okay, good to know. So Dr. Nara, the question is from Shoshana again. She wants to know, when you start a structure and you have your design, how do you start to build?
That's a good question. Here I'm assuming, or the answer I'm gonna give is related to 3D printing, like how we build it using 3D printing process. So there are some decisions we make once we have a design. And if we know what material we are going to use. That is, are you going to use a polymer? Are you going to use a ceramic? Are you going to use a metal? So based on the material we use, we can select the manufacturing process. And here I'm referring to 3D printing based manufacturing process. So once we know the material and the manufacturing process, then we start making decisions, ideally optimal decisions about how much, like how many layers do we need to print this part? Like at what speed do we want to print each layer? Like if we are printing something like I should have got some demo parts. So if we are printing something like a water bottle, are we going to print it this way, or are we going to orient it this way? So, or are we going to orient it this way? So there are decisions that we need to make regarding the placement of the part on the plate on which we are doing the fabrication. And we have to make decision about what printing parameters we want to use. For instance, if we are taking a process where we are melting powder selectively to make the part, then we have to determine how much energy do we need to provide to melt the powder. So this is similar to if you are cooking, right? If you are cooking and if you put your stove on high flame versus low flame, the rate at which the butter is melting on the pan will be different. So similarly, we have to make decision on how much energy we want to supply to melt the material. So there are a number of such variables that control the manufacturing process, and we need to optimize the process such that when I say optimize, we have to pick the best parameters possible for our purpose, so that we get a good quality part, that is something that is strong. And we also want to make it faster. We all want to do things quickly, right? So we want to print faster, but at the same time, we want to print a good part. So that's where manufacturing engineering comes into picture. Like, we as engineers are now trying to make best decisions about how to make the part.
And all of your answers, you all talked about we and we and we. Engineering is a collaborative discipline in that you all have great teams that you work with. Just as an example, Dr. Nara, how many are in your team at CMU of engineers?
So I just joined CMU. So I have like 4 undergraduate researchers, and I have 2 graduate researchers in my team. But I think when we are talking about collaboration, I want to continue on the example, right? Like we are printing with a material and we are controlling the printing conditions. So to understand the material, we need to get material science and engineering expertise. To control the printing, we need mechanical engineering expertise. So when these two come together, that's when you get the best product from the 3D printer.
How about your group, Dr. Grande Gutierrez? How many are in your group, roughly?
Yeah, I just joined CMU, so I'm still building up the group. Hopefully next year it will be much bigger. But yeah, what I wanted to say, kind of like on the lines that Sneha mentioned, is that typically we work in problems that are very multidisciplinary. That is that a lot of different areas converge. For example, I work as an engineer in problems related to medicine and medical applications. So that is, I need to work with medical doctors in my team to make, and with engineers, with computational scientists, to make sure that we get into a product that meets all the criteria needed. So that's why we need different backgrounds in our team. So everyone has their own perspective, and all together we get the final product that we need.
And Alex, not to leave you out, I know you're in 2 different labs, but what are the numbers of students and team and players on your teams?
Yeah, so with the Buth lab, there's 15 of us, if I'm not mistaken. So it's a pretty good sized lab. And with that, we do a lot of additive manufacturing oriented stuff. And then with the Cheyenne lab, I believe there's currently 5 of us. And Cheyenne's lab does a lot more material science oriented work. So it's been cool getting like the combination of the 2 coming together. But yeah, like with teams, one of the fascinating things being a PhD student is it seems like everybody gets their own special thing and they become the best at that one thing, but no person is the best at everything. And so with it, since people can like grow these individual strengths, we can all together kind of build to something a bit greater than, most definitely greater than what we could do on our own. So yeah, it's definitely great having these different colleagues, and it's interesting seeing what they're doing.
Yeah, and that's a perfect segue to the end of the show. And you have no idea I'm going to ask this, but we had Mr. Manning's 4th grade class send in all those questions. And we have other young viewers watching the shows. So I'd like to throw it back out to you for one final comment. Dr. Sneha Nara, can you offer some advice to our younger viewers?
Okay, if I had to go back in time, one thing that I would change in the way I learn concepts is pausing for a bit and trying to understand the fundamentals or the basics very well before I moved on to apply it to a problem. So we are always in a rush for personal reasons or external reasons like exams, homeworks, so many things. I like during my graduate school, that's what I learned. I unlearned all the rush to apply something, and I learned to understand and being aware of, I don't know that, so I'm gonna learn about it. So just acknowledging that I don't know, it's okay, and I can learn, and then learning it. So that really helped me, and I wish I did that more even before I came to graduate school.
That's some great advice. Take your time and understand. Very nice, very nice. Dr. Grande Gutierrez, some advice for our younger students.
Yeah, I would say that thinking about what you want to do next, it's fine if you, it's great if you know, but it's also perfectly great if you don't know. You can always change and adjust later on. It's gonna be a lot of work. You're gonna have to work hard and study, but it's also supposed to be a little bit of fun. So you should enjoy a little bit what you're doing. And yeah, it's okay if you don't know. As I said earlier, I did my undergrad in aerospace engineering. Now I work in the medical field. So it's never too late to change and try different things out. Don't be afraid of trying new things.
Wonderful advice, wonderful advice. Alex, you're probably closer in age to our viewers.
Yeah, so the bit of advice that I would give, it's very similar to Gutierrez's advice, is not to be afraid of change. And kind of with that, like I know personally, I initially started off on the chemistry route, found that there were some other things that were interesting me more. And being in college, like I was concerned about timing with switching to different things. There is time to try different things and try new things, and don't be afraid of change. Do what's going to fill your cup. So even if you start doing one thing and you get very deep into it, it's never too late to change.
Again, some excellent advice. Before I conclude, Anybody want to say anything else?
Those are some really great questions.
Yeah, it was fun.
Yeah, and I enjoyed your follow-up questions are also very thoughtful.
I try to think like a fourth grader. That looks like it's about all the time we have for this show. I want to thank the three of you for being guests today and spending your afternoon with me. I would also like to thank Mr. Manning's fourth grade homeroom who sent in the questions for our show. I'd like to thank the Leonard Gelfand Center who makes this possible. And I'd like to thank you, our viewers, for taking time to watch. Bye, everyone. Stay tuned for our next episode.
Bye.